We will now use the concepts we developed in connected masses to solve problems. Let's start with this problem. A 10 kilogram box is on a ramp inclined at 37 degrees to the horizontal. What is the maximum force required to pull the box up the plane? What is the force pressing the box onto the plane? What is the normal force applied by the plane on the box? Well, it's a simple application of what we have discussed so far. We have a box that is of mass 10 kilogram on an inclined plane, inclined at an angle 37 degrees with the horizontal. Now, what is the weight of this box? The weight of the box is m times g, that is 10 kilogram times 9.8 meter per second squared, that is 98 Newton. And what is the direction of this weight? It will be acting vertically down. So the weight is 98 Newton acting vertically down. Well, this 98 Newton now has two components. What are they? There is a component mg sine theta. Well, this is mg. So that mg sine theta down the plane and mg cos theta at right angles to the plane. The component of the weight pulling the box down the plane will be mg sine theta, that is 98 sine 37 degrees, that is 59 Newton. So the force pulling the box down the plane is 59 Newton, which is 98 sine 37 degrees. What is the minimum force that is required to pull the box up the plane? Well, the minimum force, what you need to do is to balance this force. The box is being pulled down by a force of 98 sine 37 degrees, that is 59 Newton. So in order to balance that force, you need to apply an equal force up the plane. Then you are ready to move it. Well, some of you would say, but don't you need a bigger force than 59 Newton? Well, remember, if there is a net force, it's going to produce an acceleration. We want the state when the forces are balanced. So, in order to pull the box up the plane without causing acceleration, we need an equal force in the opposite direction. So the amount of force you require to pull the box up the plane is 59 Newton. That is the minimum force you require to pull it up without any acceleration. If the upward force is greater, there will be a net force. That net force will produce an acceleration. So the answer to part A is you need 59 Newton up the plane. B. What is the force pressing the box to the ramp? The box pressing the box to the ramp is this force, the component at right angles, mg cos theta, and that mg cos theta is 98 cos 37 degrees, that is 78.3 Newton. And this is the force pressing the box onto the inclined ramp. What is the C part? What is the normal force applied by the plane on the box? The normal force applied by the plane on the box will be opposite to this 98 cos 37, and that will be exactly equal to that amount of force. Alright, let's do another one. a mass 2.25 kilogram on an inclined plane, inclined at an angle theta equal to 37 degrees, is connected by a string that passes over a pulley to a mass of 1.65 kilogram hanging freely. Find the acceleration of the system of masses and the tension on the string. Well, we have now the connected masses on an inclined plane. Let's draw a diagram of that. Here is the inclined plane. The inclined plane is inclined at an angle 37 degrees. The mass 2.5 kilogram on the inclined plane is connected by means of a string to another mass of 1.65 kilogram, and that is hanging freely. Well, we need to figure out the force, the net force on each of these masses. Is that right? That's the method we developed. Isolate each object and figure out the net force on each object. Let's try that. We will assume that 1.6 kilogram mass is moving down, pulling the 2.25 kilogram up the plane. So we will assume that the system is actually moving down. That means the 1.65 kilogram is falling and the 2.25 kilogram is moving up the plane. Let's study the forces acting on the 2.25 kilogram. Now, by now you must be familiar with the forces. What are the forces acting on the 2.25 kilogram? First of all, its weight mg. Mg is, mass is 2.25 kilogram, g is 9.8. Therefore, its weight is 22.1 Newton. That is acting vertically down. The weight of the box is 22.1 Newton acting vertically down. And now, the moment you mark the weight, you must know a component of this weight will be pulling the box down the plane. What is that component? That component is mg sine theta. Mg is 22.1. So 22.1 sine 37 is the force pulling the box down. And then what is the force pressing the box onto the plane? That will be 22.1 cos 37. The force pressing 2.25 kilogram onto the plane is 22.1 cos 37. That is 17.6 Newton. So this force is 17.6 Newton. That will be 22.1 cos 37. It works out to be 17.6 Newton. And the force pulling the 2.25 kilogram down the plane will be 22.1 sine 37 degrees, and that is 13.3 Newton down the plane. Alright, what is the other force? Well, there is a force applied by the plane at right angles, and you can see that will cancel with this force. So you don't need to worry about the forces that are at right angles. What is the other force acting on this? There is a tension on this string which is pulling the box up. So the tension T on the string pulls the mass up the plane. That is the tension T. Tell me, what is now the net force on that 2.25 kilogram mass? You can see the forces at right angles cancel. So only these two forces survive. Therefore, the net force pulling the box up the plane is T minus 13.3. That is the net force. and that net force must be equal to mass times acceleration. So the net force on the 2.25 kilogram is T minus 13.3 Newton. And that net force must be equal to MA, and we have our first equation. What is that first equation? T minus 13.3, that is F net, equal to MA, 2.25 times A, and let's rewrite that equation. That will be T minus 2.25A equal to 13.3. That is our first equation. Now, let's now study the forces acting on the 1.65 kilogram mass. Tell me, what are the forces on this mass? Well, there are two forces on it. Its weight is acting vertically down. What is that weight? Weight mg is 1.65 kilogram times 9.8 meter per second squared. That is 16.2 Newton acting vertically down. That is one force on this mass. What is the other force? The other force is the tension. The tension T is up. And now, the mass is falling, which means what is the net force on that mass? The net force will be 16.2 minus T. So the net force is 16.2 Newton minus T, and this net force must be equal to mass times acceleration. F net equal to MA, the net force equal to 16.2 minus T, M equal to 1.65, A is the acceleration which we need to find. Because they are connected, acceleration of this mass is the same as the acceleration of the other mass. So we have now the equation F net equal to MA, 16.2 minus T equal to 1.65A. Rewrite that equation. What will it look like? It will be T plus 1.65A equal to 16.2. Just move the negative T to the right, and there you are. And you have two equations. T minus 2.25A is 13.3, and T plus 1.65A is 16.2. You can now solve these equations. Actually, if you want to use the calculator, you can use the method I showed you a couple of classes ago. Use a matrix. Use a 2 by 2 matrix for the left side and a 2 by 1 matrix for the right side, and find A inverse multiplied by B, and that will give you the values of T and A. So I'm going to say, solving these equations give T equal to 15 Newton and A equal to 0.7 meter per second squared. Alright? If anybody has any problems solving these equations, let me know. I'm sure you will have no trouble solving those equations. Okay, let's now